Welcome to the Knowledge Graphs seminar. Today, we are in the week 8 of the course, and our focus has been on how to evolve a knowledge graph. On Tuesday, we heard from Luna Dong and Deborah McGinnis, who primarily focused on techniques that we should keep in mind for creating large knowledge graphs that are going to last over a period of time. And today our plan is in two parts. The first part is I will give my synthesis of problems on how to evolve a knowledge graph, and my synthesis today is not very long. And in the second part of the talk, we will have Frank McSherry, who will tell us about incremental view maintenance. All right. So I will start by giving an overview of the problems in evolving a knowledge graph, and then I will look at some real-world examples that require changing the knowledge graph. I will give a listing of the change management techniques, which I have classified into three parts: schema evolution, view maintenance, and truth maintenance. I have some material on schema evolution that I will share with you, and I'm hoping Frank will give a solid overview of view maintenance. And truth maintenance is something we are keeping for future years. So the only constant in life is change. We always see changes, the real world changes, there are changing business requirements. And as these changes happen, we have to change our software artifacts. And because knowledge graph is a software artifact, we have to change it as life changes. And as things change, we could, our requirement could be affected in two different ways. One is we are revising the schema, and the other is we are revising the ground facts in our knowledge graph. So for a knowledge graph, the schema change could involve changing the semantics of the relations, or introducing new relations, or renaming relations. And we look at examples of some of those changes. And as we address those changes, we have to keep in mind both technical issues as well as social issues. By technical issues, I mean we need some algorithmic techniques using which we could apply the changes to the knowledge graph. But because knowledge graph is a piece of software, and it is used by end users as well as by software developers, there are also social issues. So we have to make sure that as we make changes, we don't break things, and the code does not break, and people who are depending on certain things to be present or not present in the knowledge graph, they are not adversely affected. I mean, the social issues and processes are clearly very important, and to some degree, we heard about those on Tuesday from Deborah. And I think today we are focusing primarily on technical or algorithmic challenges or approaches. So for the first part of my talk, I'm going to give examples. And these are examples which are synthesized from our series last year. Primarily from Hector's presentation, who talked about some of the changes that they face in the development and deployment of their Google Knowledge Graph. So just to motivate the examples of a changing world, I'm here taking the example of Amazon product graph. Same example could apply to the Google Knowledge Graph too. But in the context of the Amazon product graph, the sort that Luna was talking about on Tuesday, the world is constantly changing. We have new products, we have new product categories, we have new features that manufacturers are introducing. Some products get discontinued. And as those changes are happening in the real world, we have to keep our knowledge graph in sync with those changes. Then there are changing requirements. And this is the example that Hector gave in his presentation last year. So in Google Knowledge Graph, at one point, they had this constraint that an artist must always be a person. And then they started seeing examples in their data feed where people were specifying a Vocaloid as an artist. So Vocaloid if you don't know, is actually a computer program. And these days, computer programs could produce music. And in those cases, people would say that the artist is a Vocaloid. Now, as examples of such data started showing up in Google's data feed, they had to do something about it, because they don't control the data feed, because this is a third-party data feed. They are not doing it, and they want that data to be presented in their knowledge graph. So they have to go back and change the constraints on who can be an artist. And they were forced to update the constraint to allow even computer programs to be artists. In the music domain, in the Google Knowledge Graph, they include the artists for an album. And Hector was telling us that usually they are not able to get all the artists of an album from a single source. And they end up having to fuse information from multiple sources to get an authoritative list of artists for an album. And the data feeds that they get, they constantly keep changing. And as they change their format, they have to change their procedures using which they are incorporating the data into their knowledge graph. Then there are examples where you have computed some inferences based on certain properties of your knowledge graph, and those inferences are no longer valid. So for example, you may have a constraint that movie theater only shows movies. But under a given circumstance, it may be that people are starting to show operas. And if you look into the modern context, people are doing vaccination centers in stadiums, right? Stadiums are not just meant for sports, but they are treatment centers. And if based on those constraints, you had cached some information in your knowledge graph, and now the real world constraint has changed and different things are happening, then you have to go back and revise all the information that you had previously cached. Sometimes you have to change the schemas. So for example, you may have a knowledge graph in which you said, well, we are going to have companies, and companies are going to have a node property person. But then you know that CEO has a tenure, and CEO usually changes. And you may say that, well, no. Now we want to have a CEO as a separate object. And with that object, we're going to have properties such as name, start date, and end date. And now suddenly your schema has changed, and you have to revise the schema. And if in your knowledge graph you had some data corresponding to your old schema, you have to update that also. All right. So that was sort of a spectrum of changes that that we may face, and that was sort of a motivation and setting up the context for the techniques we are talking about. Now, for a relational database, in addition to adding or removing tuples or entries in your tables, you can do changes such as adding or removing a column, or you could rename an attribute. And in databases, such changes are known as database reorganization, because you may already have a lot of data stored on the disk, and if you're going to add and remove columns, you may have to reorganize your data just to make sure that things remain efficient. But in a knowledge graph, the schema can be a little bit more complex, and you can have changes such as adding or removing classes, adding or removing superclasses, adding or removing properties, adding and removing constraints, some examples of which we saw earlier. And many of these changes, they have been researched under the field of object-oriented databases under the heading of schema evolution. And I'm going to give you a whirlwind tour for some of the things people have tried. And the general principle underlying the techniques that have been used is to maintain certain invariants. And so we assume that system must have, or our schema must have some properties. And in some cases, we end up having to make system-specific decisions, which tend to be arbitrary. And I'll try to give you a flavor for each of these. So for example, if you remove or rename a property, then if you have lots and lots of triples stored in your knowledge graph, then you have to propagate that renaming of the property throughout the graph. And in some cases, you may want to tell user how many changes you made, and typically people would do this by generating a summary of all the changes that were applied to the knowledge graph. If you add a new class to the system, so one invariant that people usually follow is that every class would be a subclass of a system-defined root class. So if you add a new class and you don't specify where it should go, the invariant would be to just put it under the system-defined root class. Now, what happens when you remove a class? When you remove a class, things tend to be a little bit more complex. You can have a situation when you are removing a class and the immediate subclass of that class has other superclasses. So in this case, you're removing B and its immediate subclass is C, and C happens to have another superclass D, right? So this is a simple case, and the easiest solution is to just get rid of B and you don't have to do anything else, right? And it works out pretty straightforwardly. But in some cases, it is possible that the immediate subclass doesn't have any other superclass. And you have the system invariant that while you can't have orphan classes in your class hierarchy. So in this case, you have to make some decision on what you're going to do. One obvious thing is to make C a subclass of the system-defined superclass, and that would maintain the invariant that your class hierarchy remains connected. A more extreme solution might be to delete all the subclasses. So like if you delete B, then you delete C also. I mean, that's more extreme, more drastic, and most systems would prefer not to do that. Of course, not without users' explicit direction. When you're adding new superclasses, there is the question of how should you deal with the redundant links. So in this case, you have a link from C to B and B to A, and let's say you add a link from C to A. Now, the superclass relation, there is some redundancy here because we can infer that C is a subclass of A from the fact that C is a subclass of B and B is a subclass of A. We don't really need that extra link that somebody added. And people take different positions on how they should handle this kind of change. Some systems would disallow such redundant links. Some systems will not care whether you have such redundant links or not. And a related issue comes up is how do you deal with cycles? Because the semantics of the class hierarchy are that it has to be a cyclic. If somebody introduces a cycle, most systems would reject that. And then systems can differ on what sort of help they give the user in resolving that conflict. All right, so that was sort of a quick overview of schema evolution techniques as it pertains to class hierarchy or object-oriented type of representation. Now, the view maintenance is a technique from database systems. Views by itself, they are a technique used to name a certain query. We can name a query using a view, and if we like, we can store the results of the query. The data from which we are computing the query is known as the base data, and the stored results, they are referred to as the materialized view. And now if the base data changes, we have to update our view. And even though I'm explaining this in the context of database systems, it is very much applicable to knowledge graphs because you could be creating a knowledge graph by pulling information from multiple databases and creating this, this unified triple view. And if your base data changes, then you have to update this view that you have synthesized from the base data. And that's all actually I'm going to say on this topic because this is really Frank's topic for today. I don't see the problem of view maintenance being talked about a lot in the context of knowledge graph literature, but I think this is really important. Many people who are building knowledge graphs, they would solve this problem by simply recalculating their knowledge graph from the source information, which is okay in some cases. But I think when your data size is huge, you want to do something better than that. A truth maintenance is a related technique, and it's a mechanism from rule-based systems. It tracks how we are using different inference rules to derive new conclusions. And a popular implementation for a truth maintenance system is known as justification-based system. And the way that works is that every time you derive a new conclusion, it records which facts and rules did you use in deriving that conclusion. And then anytime you change any fact or any rule, then using this justification structure, you can figure out what other changes you have to make in your system. So truth maintenance is even less talked about in the context of knowledge graphs. I was thinking that maybe we should have a lecture on that in this year's series, but I decided to keep that open for future years. And with that, I will conclude sort of my section, and we'll move on to Frank's presentation. Frank is going to talk to us about incremental view maintenance. He's also currently running a company he has founded whose primary technology is incremental view maintenance. And Frank is an accomplished researcher. He's made foundational contributions in computer security. His contributions have also been recognized by awarding him a Girdle Prize, which is actually very, very impressive. So with that, Frank, I hand it over to you. Please take it away.
Excellent. Thanks very much. Let me start out the screen sharing situation first.
Yeah.
And just a moment. I'm going to click various things, and we'll see if this works. All right. Do you all see a full screen? What
Yes.
appears to be a slide?
Yes.
Wonderful. All right. Folks should feel more than welcome to ask questions as they have them. I want to caution everyone that my ability to see you all while I'm giving the presentation is limited. So whatever mechanism we have for getting me to stop and reiterate a thing, feel more than welcome to invoke that. To be honest, I'm not actually sure what that is in the sort of the webinar format, but please do feel welcome. So this is just a starter slide. I'm working at Materialize now. This is, as Vinay mentioned, a company that is largely built around the idea of incremental view maintenance and trying to make it a bit more palatable and accessible to folks who don't want to have to go and get a PhD in whatever aspects of computer science you need to understand this sort of stuff. I'll have some links later on at the end. What I'm mostly going to talk about is actual, real existing computer science projects. So you can go and try these things out, and if you think there might be a connection with what you're working on and the technology, it'd be really cool to fit them together and see if they do a thing for you. So let's start with just a motivating problem. This is going to be pretty simple, but hopefully there'll be some echoes of knowledge graphs in here. I'm going to try to keep it sort of simple though, and maybe a bit more primitive. So let's start with this is time's arrow here, going from left to right. Things happen, right? As time moves along, we have events, and the one I'm going to lean on at the moment is just pulling information out of the social networks out there. So people may tweet about things, and tweets have content. They reference topics that might be associated with their particular tweets. They also mention individuals, so people, right? People both issue the tweets. They may also mention people while also mentioning topics at the same time. It's a pretty cool data set. I don't have access to it, but you can imagine, this information exists out there, and it's very valuable in the sense that it reflects a lot of really cool information about the world. It's perhaps less prescriptive than a knowledge graph is, but we'll probably be able to stretch our minds a little bit and imagine how similar concepts can apply. So let's start with just a simple question. What's the most popular hashtag out there? And this is the type of question you could ask about data that you might be able to sort of pull out some SQL or MapReduce or even just Excel or shell script and count things up. You probably get that done pretty quickly. But someone could go make your life a little harder and say, it's not super interesting counting up popular hashtags on there. We all know that's going to be BTS or something like that. What if instead we ask people to determine the most popular hashtag by the connected component of this mention graph? Right? So different people mention other people, and you might say that sounds like an emergent social structure, something like that, little connected component of people, folks who, if we follow paths of person A tweeted at person B and accumulate within each of those connected components the hashtag, what's the most popular one there? This might be a little harder. This is the sort of thing where I would be inclined to pull out a graph processing system and start to think about how do I form connected components or describe rules that identify components and aggregate that way. Life could then be made harder still by someone saying that actually what they want this is in real time. So as the data change, you want to see live updates to these statistics as both hashtags get tweeted out there and the counts change, of course, but also as these social structures change and evolve, as people form more and more links, for example, through tweets. Hopefully at this point, this is kind of intimidating. You might think this could be really, really hard. The first two are already slightly taxing, and now if you want me to keep this continually up to date, the idea of just regularly rerunning the query is sort of out the window. But hopefully it's motivating. Hopefully you could understand that, like, with the same sort of graphical data coming in, knowledge graph, let's say, that's updating continually all over the place, you might have lots of really interesting views over this data that tell you things or keep you up to date about takes on various things in the world, people and products and various other news, for example. And keeping that fresh is super valuable. There's a massive difference between learning that a particular piece of news, let's say, is supported by a bunch of reputable news organizations now as opposed to 24 hours after the fact, that type of thing. So I'm going to, using this motivating example, try to work you up a little bit and show you some of the mechanics of how one can do incremental view maintenance. So this is sort of keeping a query, like the first two lines describe, up to date as data change. And what I'm going to talk about specifically is a programming framework that I've been responsible for and I'm a big fan of. But I'm going to use this mostly as a specific artifact to talk about, but the idea is generalized. But a framework for programming for asking questions about data that has the, I believe, compelling property that it updates its computation, updates its outputs whenever you update its inputs. So inputs in this case could be the input facts into a knowledge graph, and the computations that you describe over it, various forms of queries that you're interested in issuing, but also maintaining as the data change. So that's, sorry, it's just random builds here. Differential data flow is the name of this framework. There's a repo that it's all open source, so you can go grab it, play around with that, stuff like that. And it's based off of some work that originally showed up in Cider in 2013 and sort of been evolving since then. It has some unique characteristics that I'll call out. Mainly that it's possibly one of the best fits for incremental view maintenance for queries that involve recursion or involve traversing paths of ill-defined length, right? Which often we end up doing in graphs. So what's the story here? I'm going to pitch a little bit the framework, but hopefully this resonates a bit with folks who work with data generally. So one goal that we're going to put out there is we'd love to give people an experience, a querying experience, programming language experience, where they believe that they are writing against static collections of data, right? This is generally true across incremental view maintenance systems everywhere, which is that you want to let the person describe a view or a computation across some data without having to think about the data changing yet. The system will handle the view maintenance for you, right, and handle it automatically. Because people are just really bad at thinking about writing programs against data that change. Much easier to think about writing a program against a static collection of data and then let the system handle what to do when the data itself change. So it's the intended experience across all systems, to be honest. And just to sort of draw some cutesy pictures, we're going to think about you writing a program, your prog here, which maps from some collection of data, D, on the one hand, to some collection of results, R, on the other hand. And as I said before, this could be knowledge graphs, these could be entity attribute value triples, it could be relational data, all sorts of things, ways that you like to think of structuring your information. And the experience we're going to try to provide to the user, the person who's sitting down and is excited to use the system, is that as time increases, so like for t and all of the times out there, we want to give the experience as if we had rerun your program on whatever the input data happened to be at some time t. So the input data change. We don't know how they change. You don't know how they change. But you'd love for us to give you the experience of effectively rerunning your program moment by moment on the changing data and presenting with the output each of these times. Now, this is a bad idea. We're not actually going to rerun your computation on each of the input collections. These could be massive, right? As I imagine you know, these knowledge graphs just unbelievably substantial, and as a consequence, just even reconsidering the entire input is very expensive. So the gist in almost all of these techniques for incremental view maintenance is to think about these collections, both input and output, as changes, not as entire snapshots of the data, but as changes that arrive. Changes describe, in effect, what is the difference from the previous input that we just looked at a mere moment ago. And we're going to think of these, in this system here in particular, as being a stream of these changes. Their changes happen to be written down as triples. In this case, the triples describe, as this data, time, and diff, they describe what changed, the sort of the where of it. What is the fact that we're talking about? Where would you go and look to see the change? Sorry. The time, when did this change happen? This is, in essence, this is the t in this loop, right? So as we're moving through these times, we want to be very clear about when did a change happen. This is an important part of being correct, essentially. And this third component, this diff, describes the nature of the change. This is an easy way to think of this maybe as a +1 or a -1, indicating the fact data, whatever it was, added or removed from the collection. You may not necessarily feel super comfortable with the idea of knowledge graphs that remove facts. This is fine. It's a thing that happens. Facts, generally, you like to think of them as true, but for various reasons, you may retire pieces of information. They may have some expiration. They're only known to be true for a certain amount of time, after which you are no longer confident in them, you retire them. So negative numbers aren't the end of the world here. And likewise, like once we've elicited your query, your program, as you like, from you, we're gonna run it on the stream of changes. That's the intent. And we're gonna give you your output in a similar sort of format, right? We're gonna provide the results that you asked for. If you asked for example, these counts by connected component of hashtags, report the changes back to you of these particular counts. So, rather than show you your entire output collection over and over again, the outputs of these queries, of course, can also be massive. Right? We could certainly ask for, from each particular fact in a knowledge graph, some information about locally derivable information or parents and certain hierarchies. So we don't really want to show you the entire output collection again. It could be massive. But a system could totally imagine showing you the changes. Right? It could tell you, well, whatever we agreed on just a moment ago as the output, let's tweak that in the following way. Let's either add or remove some results from that particular collection. And so the types are the same here. The data is some particular piece of payload, the facts that you are deriving. The time is, again, t. It's this logical time that's used to correlate changes in the input to changes in the output. And then the diff is ±1 sort of thing, telling you whether things have been added, removed, or how many in many cases. So this is an abstraction for incremental view maintenance and programs of that form. You have to, for some of these things, you have to turn your head a little bit to fit it into the framework you're familiar with. But your program could be, for example, a bunch of cipher queries. It could be other data log or something like that if you like to use that for describing paths or traversals through linked data. Cool. So let me just give an example. This is the language that I'm talking about, differential data flow. It's not wildly complicated, but I'm going to try to talk through a few of the things in here to try to get a sense for the primitives that it has. And the primitives are going to be helpful for us to understand some of the techniques later on where we talk about how to maintain certain queries. The general technique, so that it's not a surprise, is that we're going to do a much better job maintaining sort of elemental operations on data and piece together these sort of simple implementations of elemental operations on data into larger, meaningful computations. So yeah, so this is super simple example that's going to turn into a graph looking computation in just a moment. Bear with me. So these, the way these programs often look is you start out by defining some inputs. These are the tables. These are going to be with us for a while, and they may change, but we're going to start with them essentially thinking of them as empty collections initially. Maybe the first change introduces lots of data, but their names are going to persist throughout the query itself. So we want to just bolt these down first and say, whatever we're about to do, it's going to be in reference to these changing collections. The next thing we're going to think about doing is describing some sort of query. I think of this as a program, but it's very reasonable to think about it as a query as well. It's something that you'd like to do to, in this case, nodes and edges that will result in some, hopefully non-trivial, like meaningful results coming out the other end. This particular example does a join, relational join between nodes and edges. And what this says is, for each of the nodes out there, go and find me an edge that starts with that same identifier. So it's essentially trying to do one hop along these edges. It's saying from each node n, find me all x's such that I have an n comma x in my collection of edges. And this could very easily be, a knowledge graph following any other sort of labeled edge that you have out there. You might restrict the edges by a particular relationship that you're looking for and follow that to find, person who knows some other person, for example. This computation, so we did a join. It's going to concatenate in the original set of nodes for reasons. Just bear with me. This is essentially saying we want to maybe go one hop out from the nodes or zero. So one or zero steps away from our original location. And then we apply this distinct operator that says, well, okay, maybe we reached the same destination twice or three different ways. That's not important to me. Let's just keep track of the set of places that we can reach along edges, starting from nodes after one hop. And we then sort of move into, having now defined our query, we move into the sort of more interactive incremental part of the computation where we get to start advancing time and we get to start playing around with these nodes and edges collections. We get to think about, in the example so far, we might add a whole bunch of data into nodes, add a bunch of data into edges. So we sort of populate them with initial nodes of interest and whatever our initial edges in our graph happen to be. And the promise of this sort of system is that the results that come out of this particular query will be updated as we perform all of these insertions. So we can be told, the set of reachable nodes has grown by the following nodes, possibly either because we added a new start to the node set, or we added a new edge that connected an already existing starting node and reaches us somewhere else. All right. Now, there's more things that you can do here. Inserting edges is fun. Removing them is also fun. So this is, I think, the common case a lot of people think of with incremental view maintenance, where the edges, sort of the links between things, are changing. People add edges, remove edges. This is your data in some sense. And if you believe what I've told you about this type of system so far, we're hoping that it's going to keep things up to date as we add and remove things. This is all promise, by the way, at the moment. We haven't actually seen the mechanics of it yet. So just if I don't get to it in a few slides, you're more than welcome to be angry. But yeah, inserting edges, removing edges, changing your data, good fun. At the same time, you can also totally add and remove things into nodes. This is in some way like seeding slightly different queries into your knowledge graph. If there are points of interest that you're interested in starting your queries from, you can also go and update that set as well. Add questions, remove questions, in effect. And what strikes me as maybe most important is you can do both of these at the same time, and things remain consistent. So this is fairly important, is that we're showing you the correct answer for the query on whatever nodes and edges happen to be at a certain time. If you update both of them, that isn't just, oh, I don't know, do one, then do the other, let's see what happens. It's very clear there's a correct answer that we should have provided. So if you, for example, remove a node and remove some incident edges to it, the reachable things on the other end of the node should just go away. That shouldn't take a little while or anything like that for them to vanish. There's a very clear correct answer that we should be seeing. Okay, so this, I don't know. I mean, everything in here is something you could have done in a relational database in the past 20 or 30 years. So we're gonna make this a little bit more interesting and a little bit more graph related. So we're going to indent roughly and talk about a different sort of operation that you might want to incrementalize. And this is, hopefully you can imagine what this might be. This is an iteration operator that takes a little fragment of logic. Right? In this case, the exact same thing we talked about, this goes 0 or 1 steps out, but repeatedly applies it to some initial set. So this computation is actually going to describe, starting from a set of nodes described by nodes, repeatedly go 1 or 0 steps out and form the set of results there, and do that indefinitely, essentially, which, if you're familiar, will form the reachable set of all nodes from the seed set nodes in there. And this is suddenly more interesting. This is something that's much more complicated to express in traditional database systems. It's a bit more in the spirit of graph processing systems, the sorts of queries that you might ask on knowledge graphs where there are potentially unbounded interconnections between the various facts that you might want to explore to reach some conclusions. This indentation that just happened here really makes incremental view maintenance hard. So up until 10 years ago or so, folks didn't really have a great story for how to do, my take at least, folks didn't have a great story for how to do incremental view maintenance on these sorts of computations, because the iteration just sort of blows your mind. It knocked out a lot of the pre-existing technology, which is too bad. Fortunately, we're going to see throughout the course of this talk how to recover that, how to get back a system that is able to maintain these computations that traverse potentially far-reaching connections through a graph. Now, I'm going to give some hints. Now, you're not supposed to fully get your head around these things, but I do want to tease a little bit where we're going. Just like before, we're going to have these streams of triples of data, time, and diff. I'd said before that the diff was an integer, +1, -1. That's going to stay true. The data in this case, they're nodes and bools. It's a pair. Maybe I should have just left that be called data. But what's interesting, the thing that's going to make our life a lot better is that the thing we were thinking of previously as time, whatever that was, it might have been integer, milliseconds or something like that. We're going to change, and we're going to think about time as being a more complicated object. So this is sort of the secret to all of these techniques, is that we're going to do our incremental computation not with respect to a line anymore. It's not just going to be the previous, then the next, then the one after it, describing diffs that way. Very standard incremental computation technique, of course. But we're going to introduce the idea of doing computation with respect to a partial order. In this case, time paired up with a round of iteration. And we'll see in some pictures in a moment, but this is going to sort of correspond to doing incremental computation over a two-dimensional grid. And for some reason, that's going to delightfully make incremental computation over iterative computations efficient and practical. And you're more than welcome to wonder, what the heck does this even mean? I'll try to show a whole bunch of brightly colored pictures that help this. The way that I kind of like, and maybe it works for people, maybe it doesn't, is one way to think about incremental computation everywhere is that we've been following this rule, that the collection of data at any point of time t should be equal to the sum over all s less or equal to that t of the differences, the changes at the time s, right? And this was true back on our previous slide where we were talking about moving time by time by time, to get to any particular collection at a moment in time, we would have accumulated up all of the changes. So this, this equation might intuitively make sense. And the thing that's surprising is that it does make a lot of sense, and that inequality sign you see, the less or equal sign, doesn't need to be just for integers. It can be much more general. It can be a partial order rather than a total order. And when you make that relaxation and rederive all of the math, a lot of really cool things make sense. A few years later they make sense. You get a lot of headaches for a little while, but then eventually things come together and you get a pretty cool computer system. All right, I'm just gonna give some examples because you might be suspicious at this point that this is a lot of theoretical nonsense. So I'm just going to throw out some numbers that are meant to be stimulating. We were just looking at a graph reachability computation, right? And this, as a computation you might apply to large data sets. It's very primitive, of course. It's literally just, can I reach other nodes? But it's sort of the essence of a lot of large-scale graph processing and graph mining. So here's some numbers. This is Sigma 2016, so this is not recent. The numbers I'll show you are from the same time, though. but these are various graph processing systems. Some of them, I think Socialite, for example, is from Stanford. And some numbers of cores of computers and some data sets that are sort of known in the community. And we can pull out differential data flow over here, that computation that you just saw on a single core, this actual laptop here. And it goes relatively fast. It's not the fastest thing here. Myria is for sure a little bit faster. But what's really cool is that the whole computation can be incrementally updated. So if you go through and you start removing facts, removing happens to be the hard thing to do in reachability queries. Adding is kind of easy. But if you start removing things, the updates take on average tens of microseconds, right? Microseconds being the thing, less than milliseconds. So this is really quite fast. And you can imagine potentially a very high throughput system at this point that can handle lots and lots of changes in times that are proportional to the number of changes you experience rather than the volume of data. Right? So you could be sitting on billions and billions of facts, but as long as the rate of change is not too high, you can keep up with it and maintain all of your results. Cool. So I'm just going to throw up a little picture just to give you some intuition for what incremental view maintenance feels like. This is a complementary cumulative frequency function, I guess. It's like a CDF spun around, and it goes from 0 to 1,000 rather than 0 to 1. But it's essentially telling us out of 1,000 samples that we took, how long did each of the updates take? They're random updates, some number of microseconds out there, which actually ends up at like 20 seconds out at the right-hand side. And one way to look at this is that, well, a lot of the time you make a change to the data and nothing happens, right? The fact that you added or removed doesn't result in any new derivation of information. And you need to check that, it's important, but often that's quite quick and you say, whoop, we're done, nothing happened. Easy times, but also not very interesting. In this case, about 60% of the time, something happened, not necessarily anything super complicated, but we had to go chase down a new fact and figure out did it lead to something, maybe go a second time, that sort of thing. And then just to call this out, yeah, things can change. Like, you can have events that substantially change the results. If an edge is added or removed in a very core location in the graph, for example, we might dramatically go and change our results. If some very famous, let's say BTS follows someone on Twitter who is me, let's say, that will dramatically change a whole bunch of reachability around me. And there's no magic there. Like if that's actually the case, if a lot of the data change, someone has to go and do all that work. Now, hopefully we're doing work that's only proportional to the computation that's changed or the results that have changed, as opposed to rescanning the entire thing. But there's no magic. There's no guarantee that a small change in the input results in a small change in the output. It may not. And that's one of the exciting things I suppose about graph computation is that, yeah, one little change can result in sort of a massive explosion of new information, which is fun. All right. I'm just going to pop back to this and just show you a few little modifications to this, just to try to, if you're not wild about reachability, there's some other variants that you can do here. As an example, so if instead of tracking which nodes that you can reach, we tweak this a little bit and say that at each node we have an integer attached to the node. So it's got a label. The label in this case is totally artificial. Maybe you start it with the node's own name, for example. And rather than just see who you can reach throughout the graph, we instead propagate the names of nodes. In particular, we propagate, every node repeatedly propagates the smallest named node that it's seen so far, the node with the smallest label. This is a classical algorithm for computing the connected components, weakly connected components of an undirected graph. That's suddenly new and interesting. It's not just can one node reach, or some nodes reach a set, but we've actually learned a structural property of the data. We found which communities can reach other communities and which communities are isolated from other communities. And it's very similar, like the same algorithm has the same incremental execution properties when we go and explore and play with it. And responds nicely to the introduction and removal of all these bits of data. So this framework, the intent at least, is that differential data flow provides these elemental operators that allow you to explore graphs. Right? You need to describe the computation, of course. But if you have, for example, certain patterns that you'd like to explore, that's generally an iterative algorithm that will repeatedly join together edges which have the right labels or labels that match certain patterns over and over and over again, unfolding the paths as long as they continue to match. You can certainly fit that into this framework, and whether it does a great job is a good question. Depends a lot on your query, but it fits. All right, so so this is what we're going to be working from is a world in which we have these sort of elemental operators, things like joining two bits of data together, some aggregations. So the distinct operator and the min operator are both aggregations that said, for a bunch of facts associated with one node, perhaps, or any other key like label, reduce the data down. And then iteration is a way to express this sort of path following or like repeated application of various rules. What does this actually look like when we try to build a system around this? Like if we wanted to implement this to both compute the answers efficiently, but then also maintain them efficiently, how does that work? And for sure, there's a few ways that you could do this. Traditional databases don't take the approach I'm about to describe. Traditional databases try to, when you update nodes and edges, they try to form a new query in the same language that says, well, if there's a delta nodes collection, what's the query I should issue in the same language to find the changes? And to be honest, it gets quite hard with these iterative computations. So we're not going to do that. We're going to do something different. So the approach we're going to look at is data flow is the name for it. And the rough idea is that we're going to take our program, which we described previously as what looked like imperative code, right? It said, take some collections, do some things to them, and then you're done, or maybe repeat them. And we're going to rewrite that as a graph. We're going to rewrite as a directed graph that describes the flow of data through our computation. Essentially, as information about nodes and edges arrive, we're going to route them to bits of logic that say, what should I do with that information? You can sort of see here that nodes and edges first get joined. We did indeed have a join between nodes and edges, and the results that came out of that were the results of matching up information about nodes and edges that emanate from it. We did have a concatenation, right? We concatenated back in the nodes to the resulting collection. And then there's some distinct operator that we applied to the end of that. You might say, well, this isn't fundamentally different, is it? And you're not wrong. It's meant to be the same expressive capability, though the important distinction here is that we've gone and become very explicit about if the only thing that I'm provided are changes to data, how do I drive my computation around, right? Instead of thinking that I might need to rerun any particular programs about, we've essentially locked down the program, right? We've said join, concat, distinct with these arrows. That's the program. That's the query. This is what we're going to do to figure things out. And now feel free to flow as much information along these nodes and edges arcs as you like. And indeed, that's exactly what we're going to do. We're going to treat each of these nodes and edges as these streams of these updates that tell us over time, how does the collection of data change? As nodes are added and removed, we'll see corresponding updates here. And as edges are added and removed, we'll see corresponding updates there. And we have to now implement these operators in a way that they respond correctly to these changes. And sometimes that's easy. Like the concat operator is super easy. We just take both of the input streams and concatenate them, put them in the output, just merge any updates there. But other operators, join and distinct, are a bit more complicated. If you're familiar with relational database joins, right? Each time you get a new entry in nodes, you have to check and see, is there anything in edges that matches it? So you probably got to keep a copy of edges around somewhere. And similarly, as new edges arrive or depart, you need to check out into nodes to see, do they match something there? Do I need to add a new match result in the output or possibly retract one that I previously emitted? And similarly, distinct is going to need to keep some state too. It needs to remember what it's previously emitted so it can know to suppress duplicates, for example. And most of what we're going to see in the state are these accumulated changes, these data time diff triples that have come by. Basically, what we're mostly doing in the operators is recording what we've seen thus far, like the accumulated inputs that have flowed into the operator. Yeah. Now, there's some nice properties here. Let's talk about a few of them. One of them, one of the cool properties, is that this work is largely data parallel. This is a term that essentially means that the description of the operators, for example, join, can be decomposed into lots of independent bits of work, right? Each of these join operators says, I'm going to do the same thing on each of the keys that might match, independent of what happens on the other keys, right? I'm going to, if two people match from emanating from node n sub 0, that's wonderful. I'm going to go and do that logic. And if something's happening at n sub 1, some other node, don't care. I mean, they can do their job independent of me, which is really cool. It gives us a few capabilities. One of the more popular capabilities is you can partition this work up between multiple workers in your system, right? So if you have a multi-threaded system or multiple processes, multiple racks of computers, these sorts of things, you can scale out a lot of work. But even more importantly, I think, especially for this talk, what this data parallelism is really describing is independence, right? It's saying these operators can be described as units of work that are independent of one another. And that means that we have a really solid basis for incremental implementations of these, right? So if something changes about node n sub 0, we know that we don't need to change anything about n sub 1, whatever was going on over there. Right? We can wait on n sub 1 until it changes. This is really helpful for decomposing these larger computations down into a bunch of independent actions that can be independently updated as well. So just to sketch this out a little bit more, I think this stuff is interesting. Hopefully you do as well. Sorry, the multiple threads and workers and stuff like that. As we move data along these data flows, if we have partitioned our state up between the different workers, we may need to do some communication. For example, going into these join operators, we may need to shuffle the edges that go in. We need to shuffle the nodes as well. Remember that the independence is only after you have gone and identified the key for the join, for example, right? If they're being matched up at node n sub 0, we have to put all of the n sub 0 data and all the n sub 0 edges in one place before we can actually do that work. The shuffling is essentially why we can't just, if a change happens to one of the nodes, we can't just say, great, we'll solve the entire problem for what n sub 0's change does for our computation. Unfortunately, those changes may propagate out to other keys, and that's sort of where this exchange causes problems. Essentially, it's the one that shuffles a bit of information around and says, whatever your changes were, we might have to go and bounce them into some other people who weren't changing. Bad luck. But it's absolutely wonderful to call them out and understand these moments in your data flow. And we have yet another one in front of distinct. Distinct, you might expect. If we want to figure out how many distinct copies, or sorry, ensure that we only produce one distinct copy of some node, n sub 0, we should probably put all the copies of n sub 0 in the same place, even if they were emitted from, as a neighbor of some other node. So this is sort of the rough structure for how you might do incremental computation on this fragment that we just talked about. Changes flow in, data time diff changes, they flow through these operators, joins, concats, and distincts, and ultimately flow out the other end. And you kind of have to trust me, I mean, we'll dive into this in the very next slide, but you have to trust me that each of these operators can be implemented correctly. And the good news is that each of them have, I think, a pretty clear spec, right, in terms of what they're supposed to produce in their output. We've already said that they're supposed to produce output changes that add up to the function applied to the accumulation of the input changes. So we've got some really specific guidance about what we need to produce as output, and it sort of becomes an engineering task to figure out how efficiently can we perform that logic. And what's kind of nice, I think, is that rather than think really hard about a complicated query, we just need to break the query down into these elemental actions that hopefully we've tricked you to do when you wrote the program in the first place. You've explained to us what are these distinct operations that you're going to apply. And as long as we incrementalize each of them, we just stick them all together, and then we have an end-to-end pipeline that is incremental in nature. Right. The next few slides, we're going to go through a pretty exciting build, I think, talking through one of these operators. Right? Distinct happens to be, I think this is surprising, one of the more complicated operators. It really calls out some of the complexity, most of the complexity in incremental computation, especially incremental computation with iteration. And so we're going to use it as an example. And almost all the other operators are simpler than it. So let's look at just a general operator. And I'm going to talk through first incremental data flow. This is not yet differential data flow. We'll get there, but this is just, imagine that we have an operator that gets changes to its input. That's all that happens. Totally ordered changes. This first change, second change, third change. They flow in. Here's some initial data, right? Data time and diff time here, let's say it's 0. It's the very first pile of changes that we've gotten for our collection, essentially telling us how does our collection start. And the operator is able to figure out what the output should be, right? We just run the operator on X, it's got some logic, and we're going to produce some output data that is a diff from the previous empty collection. It's basically just announcing the output Y in this case. Now, that's great. Some more data shows up, or some changes, I should say, show up, some DX. And it's reasonable to say, what should we do now? But really, our hands are tied. If someone shows up with some DX, the input is now the accumulation of DX and X. And the only thing that we can produce in the output is the solution, essentially, for, well, let's think about applying our operator to the accumulated input and subtract off whatever we previously output. That's the change that we need to produce in the output. And hopefully we don't compute it this way necessarily, but we know what we need to produce, at least in terms of the output. Now, this can repeat, right? We repeatedly get more changes to our inputs. There's another corresponding change we need to produce to our output. At every moment, our hands are tied. And there's a very specific result that we need to produce. And we just keep doing that, right? Like there's no real degrees of freedom. Now, that's incremental data flow. You can, if you have such an operator that only ever receives changes to its inputs and needs to produce changes to its outputs, works great. You can build a nice big data flow of all these things, directed acyclic data flow of all of these things, and no worries. Cool. Something else that you can do, this is not meant to be satisfying. Well, I'll show this dissatisfying in just a moment. But another thing that you can do that people have done for a while, particularly in data log, so semi-naive bottom-up data log evaluation, takes very similar primitives and just says, you know what, let's put a little loop here, basically. They have more complicated data flow graphs in here, but morally, we'll do some data flow computation, imagine this operator or some collection of them derives some facts. There's some input facts over as X and some output facts that get derived, represented as Y. And these systems, in general, like derivation on graphs generally, say, well, I'll start deriving some facts, like I've got some base facts and you've given me some rules to derive more information. I'll start deriving that additional information and I might reach even more facts after that. Like those, if I fold those facts back into my input, I can continue. And essentially what they do is they continue until they run out of new facts to derive, right? So you might start with your facts X, produce some output facts Y, maybe that feeds back around. We might take Y and remove X so that we don't introduce redundant facts, ones that we already know. But the process will continue essentially until it quiesces. So this is a decent way to describe an iterative computation, an efficient iterative computation on a graph sort of data, but a static bit of graph data. So yeah, sorry, this is essentially semi-naive bottom-up data log, if you're familiar with that, or various other approaches to traversal graph mining. Right, now the difference is going to come in from what if you want to do both of these at the same time? And this is where differential data flow shows up, and we're going to see a bunch of pictures to try to call out, whoa, the cool thing that happens. If you want to do both of these at the same time, that is, have an iterative computation that you incrementally update, you can't just use the previous technology, right? If you had your fact deriving cycle going on, for example, and then you just retracted an input fact, for example, that doesn't necessarily retract the derived facts. We might conclude that A is connected to B, is connected to C, is connected back to A. And if we delete the information that A is connected to B, we might have forgotten how we knew that, and we still think that A is connected to C. And no amount of continuing to just derive new positive facts is going to fix the fact that, unfortunately, A connected to B was the kernel for all of this, right? That was what led to these derivations. We need to find some way to unroll and unravel all of our derivations. It can be really complicated. I'm going to show some pictures that might suggest that it's not so complicated. I mean, it's complicated, don't trust me, but the pictures at least look nice and have bright primary colors.
So Frank, just wanted to do a time check. How much more?
Yeah. I think there's probably 5 to 10 minutes.
Yeah, that's perfect. That's perfect.
Cool. Yep. This slide is the sort of the punchy slide that if we get through this is the one that hopefully everyone is well, I don't know, has an intuition for what's changed in the world that makes maintaining incremental computations easier. So So here's a, let's imagine it was an iterative computation. Changes in our inputs matched by changes in our outputs. They went off screen, back around. And now someone would like to change our input again. Someone wants to change X. I've just said that we can't simply append some more green boxes because that doesn't do the right thing. But we can do a thing. We can just change in a different direction, essentially, right? We can say, I've got a change for you, operator. And it's going to be a change to your first round of derivation. I'm just going to visually offset it down here. And we can apply the same rule, right? We should add up X and dx and produce some new output. You might say, well, what do we, but if we're allowed to offset things visually in the input, we can also visually offset them in the output. We can describe the output change as being to the first round of iteration, but a second round of change to the input, for example. So spatially, it's indexed a little differently. And we populate that just as we would have before. Apply the operator, subtract y. So that sort of makes sense. And this next thing is the really exciting, like the thing that folks hadn't been doing before, which is we can continue this process not by going straight down, right? We can imagine just continuing straight down and saying, well, we can keep changing that first thing over and over again. But let's think of what happens if we introduce a new change here that is meant to be a change to the second round of derivation, diffed essentially from this newly changed input. So it's sort of a change, one quantum of change in each of these directions. We can do the same math where we draw a box that is I think a little surprising, at least. It includes both changes from the very first iterative computation, as well as the preliminary changes to the first round of iteration, where we see a new change come in at this sort of filling out this square, and we do the same math that we would absolutely have done, accumulate up the x's, the green stuff, and figure out how to solve for the purple stuff. And what we're doing now is where we would previously have had sums that only had integer valued indexes, and we would just add things up that way. We're doing something that looks a fair bit more like two-dimensional integrals at this point. And this ends up being really valuable and really important. Possibly like the most important thing about the slide, if you look at it, is that the green dx box that is not included in the orange region, that's information changes that have happened for sure, but we are showing restraint and we're not including them in our computation. We know they're not relevant yet, even though we know they will eventually happen. By holding them back, we're able to update the correct part of the computation, the second round of derivation, without having it contaminated by facts that really don't belong there yet and only would confuse us. All right, so that's visually, this is, I would say, the main fundamental change that's gone on with incremental view maintenance for iterative computations. You can repeat this process essentially going down indefinitely, continually keeping up to date all these iterative computations, where the key is that you index the changes when they happen using 2 dimensions instead of just 1 dimension. And that's fundamentally the sort of key insight here, is to make sure that every time we have one of these changes, but either in the input or the output, we explicitly record down a time. It's not just, oh, it happened, let's apply it and be done with it. We want to explicitly record these things down with a time at which they happen. And there's a whole bunch of interesting analogies here. I think they're interesting. To differentiation on a discrete partial order. If you're into math, this is related to Mobius inversion. So it's Mobius inversion theorem that's related to integration on partial orders. That's all I'm going to say about that. Now, I've sketched a few of these things before, but just to sort of wind down how all this works, the data parallel operators have this really pleasant property that you can do them independently, of course, but as changes happen only to subsets of the records, we just don't need to do nearly as much work, right? We don't need to update things that haven't changed, and that's a very appealing property. Makes all this efficient. Basically, this is what makes this take time proportional to the changes, the volume of changes, rather than the entire collection a second time. And you might ask, well, how do you implement all this stuff? And really, it's not super complicated. Internally, we keep histories. Essentially, for each of these keys, we keep a history at each of the times input and output changes. And as we get new inputs that change, we reassemble the collection at the relevant time, figure out an answer and ship the result, and fold it into the history. Yeah. This is, of course, a sketch things are a bit more complicated than this, but you can sort of imagine at this point that it's largely engineering. The histories do grow without bound, and all that I'm going to throw up is there's some theorems that say if we're clever about knowing what work we might need to do in the future, we can compact all of these results down to concise representations that retain all of the relevant historical detail, but don't say too much more than we need to have. These are in a paper. Feel free to ask if you've got questions about these. I can also throw the citation at you. They're all relatively simple. They'll be in the slides too, which I'll happily share. That's the whole theorem statements and proofs. They're quite short actually, and so visually, this just brings things up. All right, so I'm going to close just with some numbers. I talked a bunch about connected components on this Twitter mentioned graph. I used to be at Microsoft Research a while back, and we did actually have access to some Twitter data. And this is some information about doing that connected component style thing where we spill out from various people on the graph of people tweeting at other people. So this describes a graph in which we can find connected components. It's exactly what we're doing in this computation a few different ways. So the black line, for example, is the number of records that we bump into if we reevaluate the full computation every from scratch. Basically, each time this iterative process takes 23 iterations, it turns out, and if we rerun the logic each time through the iterative computation, it's a flat line. There's this red line which describes the incremental implementation of this, right? Which is the one that says, hold on, let's think about diffs relative to previous moments in time. And this is the one that would say, as we propagate out, for example, those labels that we described earlier, this would only talk about labels that have changed. You can see that actually it spikes up above stateless because there are moments where the changes are more complicated than starting over from scratch. And it's a thing that happens for sure. If your data changed too much, incremental stuff is actually worse than starting from scratch. There's this cool prioritized line. I'm not going to say too much about that. It's basically like you can start to do some clever stuff in this space. But when we actually dive down into differential updates, these are when we've admitted 1 more second worth of tweets to the computation and want to re-update our incremental computation. Previously, we would have to either start over from scratch, do the stateless thing, start over from scratch and run incremental computation from scratch, or as you can sort of see here, this differential technique gets us down just into like tens of updates across the entire computation. And it translates to actual performance benefits. So this graph structure is computed and maintained in milliseconds, basically, as the data change. Taking a millisecond to respond to a 1 second change is pretty cool, I guess. I guess we had a whole second we could have used, but it gives us some spare time to do additional work as well, run some other queries at the same time. That's just about it. I suppose I should, there's some open questions. I'm going to throw these up. If folks would like, I'm more than happy to answer questions about these things. These are a bit more of like what actually causes your head to hurt when you need to go and build a real system about. This is basically like a little bit of reality about changes. Changes are not just their world was like this and then it changed a little bit. The world is, unfortunately, for example, continually changing whether you want it to or not. And you can't tell it to slow down and stop. You have to figure out how to respond to overload in that case, and that sucks. But let me just close with a whole bunch of links. Throw these up here. And these are places, Timely Data Flow is sort of the project that is the base for a lot of this work. There's a differential data flow repo, Timely Data Flow repo, and some other related stuff attached to the project. It's all open source. There's docs there. There's academic publications we've written. You can also reach out to me. You can wander over to Materialize. That's where I am. I'm also on Twitter at Frank McSherry. I'm also right here right now, so if folks have questions. This is the end of the talk, and I'd be delighted to take any questions that folks have, or let you go about your business if you're exhausted.
Yeah, so thanks, Frank. We have about 10 minutes for questions. So thanks for giving that overview. And in our previous lectures, we have talked about graph computations, and connected components is definitely a core computation you want to do with the knowledge graphs. And so in that sense, I think what you showed is clearly relevant, that let's say you have a huge graph and you computed connecting components and the graph changes a little bit. How would you get the updated connected component, right? So, and I think you're saying that well, instead of just calculating it from the scratch, you would do an incremental computation using these data flows that you were showing, right?
Yep,
Now,
for sure.
Yeah.
There are, just in case, I mean, this almost certainly wasn't explicitly called out, but this is, of course, one of the simplest examples. I was at ETH for a few years, and one of the first things that people there were interested in was a medical ontology data set that they had that described various diagnoses and symptoms and potential causes and stuff. And they were very interested in running some rule mining over that to figure out what are there are certain circumstances you could find that would describe bad data, essentially, that this would be an impossibility or something like that if they could find certain cycles or what have you. And it's basically just a very large it's ontology, a knowledge graph underlying it. And their goal was to repeatedly identify and remove these faulty facts. And they're basically in this exact situation of it's more complicated and connected components for sure, but they were able to describe it using data log rules. And this was eye-opening for them, at least.
Right. Yeah, and I think in sort of more advanced application, like take something like taxonomic reasoning. So in taxonomic reasoning, we have this operation, get me all the subclasses of a class. Okay. And typically what you want to do is you want to just calculate a transitive closure over your class graph to figure out what are the subclasses of that class. And if your taxonomy changes, what should you do? Right. So, I mean, typically taxonomies are not huge and people are okay just recalculating the whole thing, but it's the same problem, right? You have to incrementally update your transitive closure, for example.
Absolutely. Yeah. And you're absolutely right that there are going to be a lot of these situations where, sorry, I didn't realize my light was so bright here. There are going to be a lot of these situations where maybe the data aren't even so big. What's the problem? Like, is there really an issue? And I think it's a great question when you're thinking about solving problems. Do you really need this technology to solve the problem? And it's a very big trade-off between how valuable is it to have fresh data? Everyone wants some amount of fresh data, of course, but just how valuable is it, right? Is it important enough to set up a complicated system?
Right.
Versus how big is the data? How easy would it be just to start over from scratch?
So do you have any insight into how big the data has to be before incremental computation to be useful?
It really doesn't have to be that big. It depends. Again, it depends on this value trade-off. So we've got some folks that we're working with, I would say not even very big, millions of records, but they have very serious constraints about, they have some complicated computations and very serious constraints about how fast, basically every millisecond that they don't respond to a change in the data is some opportunity lost. At the risk of sounding a bit too base, like there's large industries out there that if you can beat the person next to you by a millisecond, you walk away with all the money, for example. And that's very exciting for some people. And if you can do something sophisticated and keep it fast, that's really exciting as well. So it doesn't need to be, it's not simply, I have terabytes of data and I want to be able to handle any change by the end of the week. There's for sure a large class of people who have even modest amounts of data, but want to be able to keep it up to date millisecond by millisecond.
Yeah. So there was one question from Anand, given that Anand is on the panel today. Anand, do you want to just ask directly? The question was, is there a way to only get diff from Wikidata nightly? What is the best practice to keep KG synced with Wikidata? I think he's basically talking about the use case where you build a KG by importing data from, say, multiple sources, and those sources are changing, right? Yeah. And how do you keep your integrated version in sync with the changing base sources?
Yeah, it's a good question. Unfortunately, it depends quite a bit on whether the source of data has done the work to make sure that their data are available in a syncable form. Like like Wikipedia, for example, you can tail a change log. You can sort of go to a URL and it'll repeatedly tell you what are the changes that are currently underway on Wikipedia. That's great. It doesn't tell you what Wikipedia started at, unfortunately. So it's a little awkward to first collect the snapshot that you'd like to start from and then see the changes going forward from that. There's maybe a related question. It's probably not exactly what you're looking for. There's an area of databases, subfield about change data capture. How do you record the changes that data have undergone in a way that is clear and unambiguous and it does everything you need to do? Like it keeps track of snapshots that you started from and then ongoing evolution of the data. And fancier stuff absolutely will include schema changes and other things like that to describe why your data looks different now than it did at the start. And I would say that's underway. There aren't brilliant best practices there. For sure, it's really hard for various sources, Wikidata, I imagine, to give you a snapshot just whenever you ask, right? To have someone show up and say, I'd like to see your changes, but first, please let me download the entirety of your data. So it's a little tricky.
So the short answer is that for this technique to work on Wikidata, we first would have to get from Wikidata the changes. Like if they only give us the dump, then it's right? It's not giving us the information in the right format.
That's a great point that I totally forgot to mention. No, first you have to have people who are even on board with the idea that changes are an important thing to surface. The good news, I think, is that a lot of people are starting to go in that direction now because they realize that changes are a lot more efficient when people ask for information. So if they have to give you a dump each time that you ask, and that eats up all of their bandwidth, they're a little bit happier suddenly giving you information about the changes instead.
Right.
So just for economic reasons, a bunch of data providers have started to think about moving into that direction. But it's still some time, I think, before we get everyone really on board with this is what a standard is for providing clear and concise historical information and changes going forward.
Yeah, so if somebody is not providing the differences to you, then and then if you are forced to calculate the differences yourself, would
it's an interesting question. So that sounds like almost a very unfortunate situation if you have to compute the changes yourself. Though, it is sometimes we can hopefully agree that if you had a old data and a new input data, you could probably do a diff and figure out what the changes were. It is still sometimes kind of valuable to push those changes through a computation just to see what the changes in the output look like. So if you have a computation that's more complicated than just reading the input, right? If you're going to do some complicated graph traversals, actually, I just mentioned in the comments, PageRank is a good example where you're going to end up doing more work than just looking at the input graph once. So if you have an incremental computation, you can do the diff first and then push the changes through. There's some other nice qualitative properties of incremental algorithms. One of them is you get told when there are changes and otherwise you keep quiet, right? And this is really helpful for a lot of people trying to build data infrastructure, for example, where rather than continually repull things and constantly rerun all over the place, your systems can wait to be told that something exciting has happened. And so like if you're building a fraud system, for example, it's great to be able, instead of continually asking second by second, is there fraud? Is there fraud? Is there fraud? You can wait to be told, whoa, there's a change now. Suddenly there's a fraudulent record where there was not previously one. And it makes the design of downstream systems a lot more tractable and reasonable. So there's some qualitative benefits as well to thinking about converting information into this incremental form that allows you to build reactive systems rather than polling systems. Yeah.
Naren, Mike, you guys, any questions, comments?
Sure. So I work mostly in the machine learning field, and the similar things that we're trying to do is when the data changes, how much data changed, and will it actually impact the sufficient statistics to actually change the model? Those kind of things. Are you doing something in that space?
It's a great question. And the answer, unfortunately, is kind of negative in that there's, I don't call them two schools of thought, but there are two different classes of techniques that folks use. What we end up doing a lot with is incremental computation where the changes are very discrete. They're either a change or not in various locations. And I would say that a lot of machine learning, the mathematics for incremental updates rely a bit more on continuous mathematics. Right? They generally say that like a small change to some part of a distribution might influence, whatever you're going to support vectors one way or gradients some other way. There are some connections to some more discrete forms of machine learning. So random forests, for example, or things like ID3 make very combinatorial decisions and produce structures that are very combinatorial in nature. And you can describe these in these sorts of frameworks, and they will respond kind of the way you'd hope, where like if you add some more labeled examples, if they don't change any thresholds about which attributes you decide are most exciting, yeah, nothing changes. I mean, the algorithm largely remains unchanged. Though there's a huge class of machine learning algorithms based on continuous mathematics, where if you change one record, yeah, it's not much of a change, but the gradient has changed by some epsilon in every single coordinate. And the sorts of systems that I work with generally would say, well, that's too bad. The whole thing is different now. I guess we have to go and reevaluate plus this new floating point number on everything, because we have no idea that a floating point number with a small change added into a sum gives a small change in the output. It's not a concept that we have our heads around.
Okay, thank you.
So yeah, sorry.
Yeah. Any comments from you, Mike?
No, thanks.
All right. So we are pretty much at the end of the class time. So thanks, Frank, so much for coming and giving us great presentation. Easy to understand, very visual, and it's fairly unique. You know, not many people actually work on this, but I've been interested in incremental algorithms for a long time, and it's great to see that you are really making technology out of it.
Excellent. I should actually just random shout out for the last moment then. You had mentioned earlier that truth maintenance was also a complicated thing that folks are looking at. And there's a really cool paper that folks should read out there, data log debugging for mere mortals, which uses rule systems, like uses these systems to derive their own provenance and lineage.
Okay.
And you can actually do them, if you want, in differential data flow, which means that they will be incrementally updated and maintained as your data change. Some pretty cool stuff if folks want to look into that. I'm more than happy to give you some links on the side, and you can terrorize people with them. But there's some cool stories there.
Yeah. No. I'll definitely look it up. You know, maybe differential data flow could be a core technology which can be used for both view maintenance and for truth maintenance. Yeah, that could be really cool.
Yeah, and the link is in the chat now. This is Yanis Smaragakis's and a few other folks' cool paper. Super easy to read too, by the way, about how to do provenance and lineage using data log.
Okay. All right. So thanks again. I'm glad we got to meet you, and the class got to hear from you about the.
Thank you very much.
Yeah, and
it's great to have the opportunity.
Yes. Thank you very much. And as far as our class is concerned, we'll continue next Tuesday. And next Tuesday, our focus is on what are some high-value use cases of knowledge graphs. So thank you very much, and we'll see you next Tuesday.
Thank you, Frank.